Learning Outcome 8.3. Describe and draw the block diagram for amplitude modulation and synchronous demodulation. With Learning Outcome 8.6, determine the spectrum for all signals in an amplitude modulation process. The modulation part of amplitude modulation was introduced in Learning Outcome 8.2. There, a time signal is multiplied by a sinusoid, particularly a cosine, to produce an amplitude modulated signal. You can see the amplitude of our original signal in this resulting signal. We also saw that our original spectrum was convolved with two impulses that are associated with our sinusoid. And that shifted our spectrum and scaled its amplitude. Now, what do we need to do once we've modulated it so we can get our original time signal or our original spectrum back? For synchronous demodulation, we're going to look at the case of what do we need to do to get our original spectrum at the output. So we'll therefore not look in the time domain. We're only going to look in the frequency domain in order to get our original spectrum. So the modulation is passed. We already have our modulated spectrum. What do we need to do? Well, there's a couple different options here. We're looking for this spectrum, which is centered at 0. But at 0, there's nothing here. I can see the triangular shape here and here, but it's not where we want it at 0. Looking in your book, Table 4.1, there is a frequency shifting property, which says take our time signal and multiply it by a complex exponential, and our frequency will shift. So we can take a complex exponential, which has a spectrum of an impulse. And if we look focusing on this first spectrum component, the one on the left, after we do the frequency shifting, it shifts to the right by an amount omega 1. We now need to relabel all our frequencies. So each of these frequencies gets incremented by omega 1. So on the right, we have omega 1 plus omega 1, or 2 omega 1. We know that the boundaries of each of these spectral components is omega m away from its center. So 0 plus omega m, 0 minus omega m, 2 omega 1 plus omega m, 2 omega 1 minus omega m. And because the amplitude is 1/2, and we desire to return to an amplitude of 1, we need to include a gain of 2. And that will scale it to an amplitude of 1. Okay, getting closer, we now have our triangle centered around 0, but we've also got a little bit left over. Therefore, we need to filter it, and a low-pass filter that goes just slightly beyond the boundary of where our desired signal is present should do the trick. That makes the other part go away, and we now have our desired original spectrum back. But that said, we looked at shifting this one. We have an equal opportunity to shift this one. So if instead we were to multiply by e to the negative j omega 1t, our impulse is now at negative omega 1. We're now going to do still frequency shifting, but in the other direction. So now this element is the one that will return to our desired location. Again, we need to relabel all our frequencies. Everything is decreased by omega 1. And when we note that the amplitude is 1/2, we know that we need to give it a gain of 2, which will now mean our signal has the desired amplitude of 1. Again, we need to apply a low-pass filter to remove the part that's not of interest to us. So what's the right approach? Should we shift this to the right or shift this to the left? Well, what if we did both? We add the two results. We don't need the gain. But we can also divide it by 2. We can take the average of the two, take both options. That does decrease our amplitudes again. Does this term look familiar? That's the cosine. Because you have a cosine in your signal generator in the lab, it's something we can generate. Cosine is also a real signal. It's a lot easier for us to generate real signals than complex or imaginary signals, although we've got really good techniques for doing that when we need to. Each of these alone would be an imaginary signal, a complex signal, and therefore harder to realize. But by combining them, it's a lot easier in practice to realize. And that again means we have the two impulses. And because our amplitude was decreased when we averaged, we again need that gain of 2 to return our amplitude back to 1. We still need a filter, and that will make both those side bands go away. And now we've successfully retrieved our initial spectrum. And if we have the initial spectrum, we also have the initial time signal. So let's review. We start with some signal. We care about the time signal, but it has an associated spectrum. We modulate by multiplying by a cosine. That gives us an amplitude modulated time signal. We can demodulate by multiplying by another cosine, which will then have that spectrum. We usually apply the filter first, which removes the two sidebands, and then we give it a gain. And now we have our original time signal and our original frequency signal. Even though we were thinking about the process, just by looking at it in the frequency domain, the time domain signal is also returned. That part of the process is the modulation part of the process. That part of the process is our synchronous demodulation part of the process. Synchronous because our cosine for demodulation has to have exactly the same phase as our cosine that was used in modulation. And this can be a little bit tricky to achieve in practice, because usually your radio at home is far away from the radio at the radio station. We'll talk about that later. Note that along the way, we've been talking about what the spectrum was for every signal in this diagram, in this whole process. Make sure that you can start with something and you can draw each of these spectra, not by memorizing them, not by looking at them on your note sheet, but by knowing what happens in each of these operations in doing each of these processes.